Okay, so good morning, everyone, or good afternoon for the people in Asia. So we are pleased to welcome Koike from Osaka City University, who will give us a talk on the complement of hypersurface with flat normal bundle, which corresponds to a semipositive line bundle. Very long title. Okay, Koike, so it's
sorry about that. Okay, thank you. And first of all, I'd like to thank the organizers for giving me this special opportunity. Yeah, actually, yeah, as I said, this is my very, very first time to give a Zoom talk, so I'm a bit nervous about it, but
you're relaxed.
Really? Okay, let me start.
You can show your face, so we will.
Really? But
yeah, you can show your
face. iPad, so.
Okay.
Can you see it?
Yeah.
Okay, this is my title page. So, okay, so let me start. This talk is based on the archive paper 2009-07-0656. I submitted in the last September, and I reversed it in, I forgot it, but anyway, it's version 2. Okay, my talk consists of 4 sections. In the introduction, I will explain my interest and motivation, and I will also explain what is our main results. And the rest, the other 3 sections are devoted to the proof of the main result. So let me start from introduction. Let X be a complex manifold. Here is my interest. The first one is the relation between Hermitian metrics on line bundles of X and the complex analytic structure of X. And the second one is the displacement, or what can I say? How move a complex submanifold Y in X, and the complex analytic structure of the complement X z minus Y. The first motivation is, I guess it is easy to explain. The first one is motivated by Kähler's embedding theorem. It states for the structures of the manifold if there is positive line bundle. So my question is, how is the case where there is a line bundle with semi-positive line bundle? Line bundle with Hermitian metric with semi-positive curvature tensor. So here I will explain on the second interest or motivation. For simplicity, when X is a surface and Y is a compact curve. First, I will explain the case where the normal bundle, this is holomorphic normal bundle of Y. The normal bundle is positive. In this case, Y likely to move. Actually, it moves with this dimensional degrees of freedom by Kähler's theory, replacement theory, if I understand correctly. And Y admits a fundamental system of strongly skewed concave neighborhoods. This is by Osamu Suzuki. So the situation is like this. When the normal boundary is positive, here is Y, and neighborhoods are, in some sense, concave. So the complements should convex. Oppositely, when the normal boundary is negative, in this case, Y never moves. And in this case, Y admits a fundamental system of strongly skewed convex neighborhoods. So everything is opposite. Here's Y, and the neighborhoods are should convex. So the complements are concave in some sense. And actually, it is the consequences from Grauer's theory, Hans Grauer's theory. And actually, he showed that Y can be contracted indices, in this case, in the sense of Lemert map. So my question is, how is the case where the normal boundary is flat and the degrees go to 0? For example, when Y is a curve. How is the case where Y is a compact curve holomorphically embedded in a surface X with, I mean, said that the normal boundary is topologically trivial or unitary flat? I mean, the conclusion is a bit complicated. So I would like to explain it by using these concrete examples. Let R be an elliptic curve, and let L be a flat line bundle over R, and let this one be an exact sequence of holomorphic vector bundles on R, where this one, IR, stands for the holomorphically trivial line bundle. So this one is line bundle, and L is flat line bundle. So E is a vector bundle over R of rank 2. Denote by X the ruled surface correspond to E, and denote by Y the section which correspond to this topologically trivial line bundle. So X is a ruled surface over R, and Y is a section. Case 1, it is the case where R is not holomorphically trivial. L is not holomorphically trivial. In this case, the exact sequence automatically splits. It is very simple. It's very simply follows from the calculation of extension classes. The extension class. A neighborhood of Y is by holomorphic to a neighborhood of the zero section of the dual of L. So the complement X set minus Y is by holomorphic to L. So everything is very, very clear in this case. And any holomorphic line bundle on X set minus Y is constant because this L admits natural holomorphic foliation, which correspond to the unitary representation of the fundamental group of R. And in some sense, it is Trojan, which means that L admits many Levi-flat hypersurfaces, such that any leaf is dense.
So I have a question.
Sorry.
So what is the exact sequence split in this case?
I mean, in this case.
Yeah, why the exact sequence splits here? So
okay. Actually, in this case, this exact sequence corresponds to some extension class. Scheduled in this one. I L. And it is isomorphic to H1 of R L. And this one is elliptic curve. Sorry.
No,
this one is elliptic curve. And this one is unitary flat, but not trivial line bundle. That is why it vanishes in this case. So anyway, case 1 is this kind of thing. I mean, this kind of case. So the structure, complex analytic structure of the complement is very clear. But on the complement, there is no non-constant holomorphic function. On the other hand, in case 2 is the case where L is analytically, I mean, holomorphically trivial, and the exact sequence splits. In this case, everything is of course clear. X is by holomorphic to R times P1, and the complement is biholomorphic to R times C, complex plane. But there's a difference. Actually, on the complements, there are many holomorphic functions because C has many holomorphic functions. So case 1 and case 2 is quite similar in geometrical sense, but from complex analytical point of view, there's difference between case 1 and case 2. And the remaining case is case 3. In this case, case 3 is the case where the exact sequence does not split. This case is well-known example, which is called Kähler's example. And the normal boundary of Y is analytically, holomorphically trivial, and the complement is biholomorphic to C star times C star, where C star stands for the set C, set minus the origin. So it is Stein. So case 3 is quite different from case 1 and case 2. So what I wanted to explain by using this example is there are many cases, many kinds of phenomena occurs in the case where the normal boundary is flat. Okay. In this talk, I want to explain this kind of different phenomena from the viewpoint of the metric semipositivity of the line boundary Y. For the examples in the previous page, let us consider the semipositivity of Y, where Y is, this one is a holomorphic line boundary which corresponds to the divisor Y. And I'm talking about semipositivity in this sense, definition. We say that a holomorphic line boundary L on a complex manifold X is CR semipositive if L admits a Hermitian metric of class CR, R runs and integers or infinity or omega. C omega stands for the real analyticity. Whose Chern curvature tensor is positive semi-definite at any point. Okay, in the previous examples, in case 1, case 2, the Y is C omega semi-positive because the fiber was when you study metric is well defined and it defines a real analytic Hermitian metric on Y with semi-positive curvature. Actually, in case 1 and case 2, the transition functions of fiber coordinates of the ruled surface are represented by using unitary rotation. And when you study metric is unitary rotation invariant metric. So that's why this kind of metric is well defined in case 1 and case 2. But it is not the case in case 3. Actually, in this case, it is known that Y is not even C0 semi-positive. It is first shown in Romari Petanel Snyder's paper. So we can see this kind of summary or table. But for explaining what is this, I'd like to shortly explain Ueda's classification and compare it with the semipositivity of Y. Professor Tetsuo Ueda classifies the pair Y and X, where X is a complex manifold and Y is a compact non-singular hypersurface. Said that normal boundary is unitary flat, which means that this line boundary comes from unitary representation of the fundamental group of Y, which means that the transition functions are unitary constants. In accordance with the compressed analytic structure of a neighborhood of Y. Let V be a small tubular neighborhood of Y. So here's Y, and V is small tubular neighborhood. In this case, the topological type of V coincides with that of Y. H1 of YU1. Here U1 is the unitary group, or more precisely, the sieve of locally constant functions valued in U1. H1 of YU1 is naturally isomorphic to H1 of V of U1. So we can interpret this isomorphism that so that for any unitary flat normal bundle N, there uniquely exists a unitary extension, which means that N tilde is the uniquely determined flat line bundle defined on V, such that the restriction of N tilde onto Y is equal to N. So, especially when we use it as, set it as the normal bundle, there uniquely exists a unitary flat normal bundle, say N tilde on V, such that N tilde restricted to Y coincides with the normal bundle. Then we will define the type of the pair Y and X. The definition is like this: 1 plus the maximum of N, such that the line bundle Y and flat extension N tilde coincide in nth order jet along Y. In case 1 and case 2, this line bundle Y and the flat extension actually coincide with each other, because it can be easily checked that the line bundle Y itself is unitary flat on a neighborhood of V, neighborhood of Y. So the type is infinity, because this one and this one coincide in any order jet along Y. However, it can also be easily checked that case 3, Sayle's example is, is of type 1. This line bundle Y and N tilde coincide in 0th order jet. When, what can I say? Y restricted to Y is equal to N tilde restricted to Y. It is clear because both of them are isomorphic to the normal bundle. But in the first order jet, it do not coincide. They do not coincide. That is, what does it mean? Okay, and the semipositivity of Y is, as we saw in the previous slide, like this. Case 1, it was C omega semipositive. Case 2, it is C omega semipositive. And case 3, it is not C0 semipositive.
Yeah. So excuse me. So could you so for the definition of CW semipositivity, that means that it's CW continuous.
You mean
so for the W here, it means that it's
real analytic.
Sure. Yeah, I wanted to write omega here. C omega semipositive.
So for the
real analytic.
Okay.
Yeah.
So for the omega, it's equals to the R here, right?
Actually, yeah.
Okay, I see. So okay, I see.
So it means that in case 1 and case 2, there exists real analytic Hermitian metric with semipositive curvature. Okay. Note that here, when Y restricted to V is unitary flat for some neighborhood V of Y, it is equivalent to the condition that the line bundle Y and N tilde coincide on the neighborhood of Y. Then Y admits a fundamental system of should-flat neighborhoods. Here, should-flat neighborhood means that the neighborhood such that the boundary is Levi-flat. So it means that there is a fundamental system of the neighborhood of Y such that their boundaries are Levi-flat. I explain what I said here in this picture. Here's X. X is a manifold of dimension n. And here's Y, a submanifold. Submanifold Y. We will denote by D, the dimension of Y. So D is equal to n minus Y because Y is hypersurface. Assume that Y restricted to a neighborhood Y is unitary flat. In this case, as this line boundary is defined by using local defining functions of Y, this condition means that on each Vj, there exists nice local defining function Wj of Y, such that on each Vjk, there exists some unitary constant Tjk, such that Tjk times Wk coincides with Wj. So, let us consider the subset defined by Wj, modulus of Wj is constant. Actually, this one is equal to the modulus of Wk because the difference can be written by using unitary constant. So this one defines hypersurface, real hypersurface, which is what I said as Levi-flat.
So you have to restriction of Wj and Wk on Y, then they are constant, or you just on a neighborhood.
Just on a neighborhood.
I mean, this holds on. So you mean Tjk is constant on a neighborhood, not only on Y, right?
Not only on Y, but also a neighborhood. That is an important part. Thank you.
I see.
Because here I'm regarding W1 over Wj as a local frame of the line boundary Y. And here I'm assuming that this one is unitary flat on the neighborhood of Y. So not only along Y, but also on the neighborhood transition unitary constant. That is an important part of this condition.
Okay.
Actually, this is the explanation why the condition that Y restricted to a neighborhood is unitary flat is important. In this case, there's nice defining functions Wj, and so as a consequence, there are many Levi-flats. That is what I wanted to explain here in the previous page. So it is a case. I mean, this kind of things happens in case 1 and case 2, but never happens in case 3, sales example. That is the difference between case 1 and 2 and case 3. Okay. From this kind of observation, I'd like to pose this conjecture in this talk. Conjecture. Let X be a complex manifold and Y be a compact hypersurface. So that's actually it is equal to the normal boundary, at least when Y is non-singular. Then the following should be equivalent. The first condition is that the line boundary Y is C infinity semipositive. The second one is there exists a neighborhood V of Y, so that the line boundary Y is restricted to a restricted to V. So this is the relation I explained in the previous slide. Actually, when the assertion, the condition 2 falls, then the condition 1 falls. It is easily shown. So the problem is the opposite side. Assume that the line boundary Y is semi-positive, I mean C infinity semi-positive, and I'd like to ask how is the neighborhood of Y? There are 3 remarks. First remark is this. Why is C infinity semi-positive if and only if there exists a neighborhood V of Y, such that the restriction is C infinity semi-positive. What I want to say here is the condition 1 is also a condition on a neighborhood of Y, very local condition. So both the first assertion and the second assertion, first condition and the second condition are conditions on a sufficiently small neighborhoods of Y. The second remark is like this. Note that there exists an example of the pair Y and X, that the line boundary Y is not C omega semi-positive, whereas there is a neighborhood V of Y, such that Y restricted to V is C omega semi-positive. Actually, this kind of example is the existence of this kind of example is shown by Brunera in his paper in 2010. Actually, this kind of example can be constructed by considering the blowing up of P2, I mean projective plane at 9 points. What I wanted to say here is if we replace C infinity with C omega, then it is not there. It is a kind of global condition. I mean, not a condition on a sufficiently small neighborhood. That is why I wrote C infinity here. The last one is like this. When X is a surface, both X and Y are non-singular, and when the normal boundary is settled in the Picard variety, but it is torsion. I mean, there exists some positive integers of that mth tensor is analytically homomorphically trivial, then the conjecture is affirmative. It is shown in my thesis, and it is one of the motivations in this conjecture or supporting evidence in some sense. Okay, so let me explain what is the main result in this talk.
I have a question. So can you explain the easier part from how briefly explain why 2 implies 1?
Actually, I will explain it in preliminary later. So, yeah. Okay. Main results. Let X be a complex manifold and Y be a non-singular hypersurface with unitary normal one. There are 3 results. The first one, Theorem A. This one. When the normal boundary is torsion, the conjecture is affirmative. It means that, namely, the following are equivalent. Following are equivalent. The assertion 1, Y is C infinity semi-positive. 2, there exists a neighborhood V of Y, but that what I wanted to write here is the same condition as the previous one. Y restricted to Y. B is unitary flat. But when the normal boundary is torsion, this condition is equivalent to this condition. There is a homomorphic function f from V to C, but that Y is a fiber. It means that Y is a maybe multiple fiber. So it states something on neighborhood things, very local things along Y, but it is a kind of statement which says the relation between semipositivity and semi-ampleness, because the condition 2 is quite similar to the semi-ample assertion. And in the previous slide, I said that when X is surface, and when X and Y are non-singular and normal boundary is torsion, then conjecture is affirmative. So theorem A is a generalization of this result. Okay, the second one, theorem B. Let X and Y be as above, I mean, like this. Then the following are equivalent. The first condition, there exists a neighborhood V of Y such that Y restricted to V is C omega semipositive. The second one, there exists a neighborhood V of Y such that Y restricted to V is unitary flat. So in theorem B, theorem B can be explained that we could show the conjecture if we replace C infinity to C omega and restrict everything to the neighborhood story of Y. And the third one is a main result for the case where X is compact Kähler. And in this talk, we regard it as main result in this talk. Let X be a compact Kähler connected manifold, and Y be a connected non-singular hypersurface of X, so that normal boundary is topologically trivial. Actually, when Y is compact Kähler, topological triviality is equivalent to unitary flatness. It is because Y is compact Kähler, Kähler-X theorem. Assume that the line boundary Y is C infinity semipositive. Then the following holds. The first assertion is the assertion for the case where the normal boundary is torsion. In this case, there exists a vibration F from X to B. B is a Riemann surface, so that Y is a maybe multiple fiber. I note that the domain of F is not a neighborhood of Y, but the total space X. That is the difference between theorem A and the theorem C. The second assertion is for the case where the normal boundary is non-torsion. In this case, the Hermitian type extension theorem holds on X set minus Y. It means that any holomorphic function defined on the neighborhood of the boundary can be extended. In this case, it can be rewarded as follows. For any neighborhood V of Y, any holomorphic function defined on V set minus Y can be extended to a holomorphic function on X set minus Y. This is theorem C. Let me explain why the Hermitian type extension suddenly appear here. Assume that the conjecture is affirmative. Then, when the normal boundary is non-torsion and Y is C infinity semipositive, then the line boundary Y restricted to a neighborhood V should be unitary flat. If conjecture is affirmative. So in this case, as I explained here, there exists Levy flat. And from the assumption that the normal boundary is non-torsion, it turns out that any leaf of the Levy foliation is dense in this Levy flat. So there exists a fundamental system of neighborhood B epsilon Y such that each boundary unitary flat hypersurface so that any leaf is dense in del of V epsilon. In this case, the Hertz extension theorem clearly holds on x set minus y because for any v, any holomorphic function on v set minus y should be constant. So constant function can be clearly extended. That's why conjecture, I mean, this second assertion follows from the conjecture. So I'd like to explain this second assertion as a kind of partial solution or one of the evidences of supporting evidence of the conjecture. Okay. In this talk, we explain the proof of Theorem C. This is the same statement as the previous page. I just repeated. In the proof, we use a pre-subharmonic function psi defined on x set minus y with logarithmic growth along y in a suitable sense, whose existence is assured by the condition that the line boundary y is C infinity semipositive. So from now on, as a preliminary for the proof of this main result C, I will explain the relation between the semipositivity of y and a pre-subharmonic function psi I'll construct from now on. And after that, I will explain the proof of Theorem C, the assertion 1, and next Theorem C, the assertion 2. Okay, so from now on, we will start the preliminary section. Assume that Y admits a Hermitian metric H of class CR with semi-positive curvature. Take a canonical section Fy of the line boundary Y on X. It means that Fy is the global section of this line boundary, such that the zero divisor of Fy coincides with the divisor Y. Then the function psi hat defined by this minus of the logarithm of the modulus or norm of Fy with respect to H is a pre-subharmonic function on X set minus Y. It can be easily checked. In what follows, we modify this function psi hat because I want to count the numbers of the number of positive eigenvalues of the complex Hessians of psi hat, denoted by chi, the function defined by this one. Then the derivative bar of chi circle psi hat is like this. Sorry, just one please. Something is strange, I guess. Psi hat. It's good. It's good. Sorry, it's good. Nothing is. It is equal to this one. This one is very, very standard formula. So if we denote it by psi prime, we have that this psi prime is also pre-subharmonic function on this domain. I mean, if t is positive, then this one is positive and this one is also positive. So this psi prime is pre-subharmonic function on the domain defined by psi hat is positive. Further, we will modify this psi prime. Denoted by lambda, the C infinity function like this. Here is R, and here is R, and here is 1, 0. Lambda is like this. Like this. It is equal to 0 around here, and it is equal to the identity function in this area. And lambda is increasing and convex. And set psi is the composition lambda circle psi prime. Then one has that psi is pre-subharmonic on x set minus y. So what was the reason why I modified this like this? When let v prime bj be an open set of x that bj intersects y, and take a local defining function wj of y. By using local weight function phi j of h with respect to a suitable local trivialization, then psi hat is like this, because psi hat is the function defined by this. And in this locus, I mean on Vj, this Fy coincides with Wj by using a suitable local trivialization. And here the local weight comes. And this function is pre-harmonic on the complement of y. And this one is pre-subharmonic because y, h has a semi-positive curvature. So, around y, I mean, if we shrink Vj if necessary, one has that psi is equal to psi prime, because around v, lambda makes any difference. And it is equal to this one by definition. So it can be calculated as like this. Thus, on Vj, one has that the derivative of psi is equal to this one. And this one is, complex Hessian of phi j is semi-positive, and positive semi-indefinite. And here, a positive eigenvalue appears. And this one is very small part. So, as a summary, what I wanted to say in the previous slide and this slide is, one has that the complex Hessian of psi has at least one positive eigenvalue at any point p in v set minus y if we shrink v if necessary for some sufficiently small neighborhood v of y. So here we constructed a PSH function psi. As it is PSH function, the complex Hessian has no negative eigenvalue. But additionally, here we have that it has at least one positive eigenvalue. This is an important part. I mean, the reason why we make this kind of small, technical modification. Anyway, if y is the line band of y is CR semi-positive, then we can construct such a pre-subharmonic function. Conversely, one can show that y is CR semi-positive if there exists a PSH function psi of class CR on x set minus y, such that psi is just as the previous one. For any point p, there exists a p in y, there exists a neighborhood Vp and a local defining function W and a pre-subharmonic harmonic function phi p such that phi is equal to minus log of the modulus of w square plus phi p. In this, if such a PSH function psi exists, then one can define a Hermitian metric A of y by this formula. I mean, we use, we use this one as a local frame and measure the norm by using this weight function. Then, as psi has logarithmic growth and Fy is canonical section, this H is actually CR Hermitian metric on Y. So roughly speaking, what we showed in this section is the condition Y is CR semi-positive if and only if there exists nice PSH function. I omit here, but and now I can answer the question why this direction, I mean this direction is easy. Actually, if y restricted to v is unitary flat, when it is unitary flat, then clearly it is semi-positive. C omega semi-positive. Because unitary flat metric is analytic Hermitian metric with semi-positive curvature. And if y, the line boundary is C omega semi-positive on the neighborhood of y, then on the neighborhood of y, we can construct this kind of pre-subharmonic function. And as I explained in the previous slide, by using a technique to use lambda, I mean this kind of cutoff function, we can extend psi not only the domain of psi. We can extend the domain of psi from v set minus y to x set minus y. That is why C infinity semi-positivity is local type condition, and why the direction 2 implies y in conjecture is clear. Not clear, but easy. Okay, this is preliminary part. So let me start the explanation of proof of main theorem 1. Actually, what we will do here is asymptotic. Consider the asymptotic expansion of psi. And consider a kind of linearization of local defining functions of y. Let me start. So here, in this section, we will show Theorem C assertion 1. So I will omit assertion 2. Let X be a compact Kähler connected manifold and Y be a connected non-singular hypersurface of X such that normal boundary is topologically trivial. Assume that the line boundary Y is C infinity semi-positive. And when normal boundary is tangent, then there exists a fibration F from X to B, so that Y is a fiber. In the proof of this assertion 1, this proposition is, plays a very important role. This one is a key proposition. Let M and R be integers such that R is larger than or equal to maximum of 3 and 2M. If the line boundary Y is CR semi-positive, then Y admits a system of local defining functions Vj, Wj of type M plus 1 in the sense of Ueda. which means that Vj covers Y. I mean, Vj covers the neighborhood of Y. And each local defining functions the transition of them unitary rotation modulo n plus 1 jet. I mean, up to n plus 1 order jet, the transition of Wj's are unitary rotation. Okay, so things are, here I have wrote, things are like this. Here's X and here's Y. Y is a hypersurface. And this one is local defining functions. And this one is unitary flat for some neighborhood of Y, if and only if Wj is equal to Tjk times Wk, actually. But if we say that this system of defining function is order, type n plus 1 or type m, we do not require that it is actually a unitary rotation, but we only require that it seems to be unitary rotation modulo mz. I mean, that modulo w powered by n plus 1. Here we remark that the type of the pair yx I explained in the introduction section can be explained that it is a maximum of m, such that there exists we can take a system of type m. Okay. Here, I explain why this key proposition is important. First, I called Ueda's theorem. Ueda showed that assume that the normal boundary is torsion. Sorry. I forgot to write it is torsion. it is torsion. So important assumption. And we assume that Y admits a system of type M for any positive integer M. Then there exists a system of local defining functions such that actually the difference is unitary rotation, or for some Tjk on each Vj intersection Vk. This is a kind of linearization theorem, and it is shown by using a technique from complex dynamics. Theorem A, the theorem for small neighborhood of Y, follows from this Ueda's theorem and key proposition, because key proposition says that if the line boundary Y is semi-positive, C infinity semi-positive, then Y admits a system of type M for any positive integer M. Next, Niemann showed in his book that if X is compact scalar and there exists some integer, positive integer mu, such that normal boundary tensor in mu times is holomorphically trivial. And there exists a system of type mu plus 1. Then there exists a fibration f from x to b. I mean, x admits a fibration such that y is a fiber. Actually, theorem C, the assertion 1, directly follows from this Niemann theorem and key proposition. Because from key proposition, from the assumption of theorem C, the assertion 1, there exists some mu such that it is holomorphically trivial. And from the key proposition, we have that for any m, there exists a system of type m. So what we have to do is just to show key proposition. Here we note that there exists an example of yx such that y admits a system of type m for any positive integer m, whereas the line boundary y restricted to v is not unitary flat for any neighborhood v of y. Such an example is constructed by Arnold Ueda. So it corresponds to a kind of Kramer type fixed point in complex dynamics. So a mysterious and difficult cases, but anyway, this kind of difficulty actually occurs if we omit this Taujoness assumption. Okay, so preparing for the proof of key proposition, we first consider the asymptotic expansion of psi. The goal of this key proposition, let m and r be integers such that r is larger than or equal to this one, and assume that y is shear semi-positive. And we want to show that y admits a system of type of local defining functions of type m plus 1. But in what follows, just for simplicity, we always assume that R is infinity. So this inequality always holds. And we run induction only on M. Assume that Y admits a Hermitian metric H with semi-positive curvature. Take a system of type 1. Regard this one as a local frame of Y on each Vj. And let this one be the expansion. Actually, Wj's are just a system of type 1. And system of type 1 always exists because the normal boundary is unitary flat. So it is Tjk Wk is equal to Wj plus something, I mean higher order term. What I wrote here is, I just declared what is higher order term. We will write the coefficient functions as by fkjn. Denoted by phi j, the local weight function of h on vj is respect to ej, I mean this one. Then, as it is unitary constant, one has that phi k is equal to this one by definition of local weight function, and it is equal to tjk ek square norm of minus log of square norm of this one, and so it is equal to, I mean, by using this expansion, it is minus log of square norm of ej plus the remaining terms. So by considering the Taylor expansion of this type of function, we can easily show that the difference phi k minus phi j is equal to fkj2 because this one starts from 2. Wj plus fkj2 bar wj bar plus higher order term. On the other hand, it follows from Taylor's theorem that there exists a function R2 of C class C infinity such that phi j is equal to phi j00 plus phi j10 times w plus phi j01 times w bar plus the remaining terms, and the remaining term goes to 0 in this order. Just a usual Taylor's theorem for the variable w. Then by using this finite Taylor expansion, we have another expression of the same function phi k minus phi j, which is phi k 00 minus phi j 00 plus phi k 10 wk minus phi j 10 wj plus the anti-holomorphic counterpart and higher order term. We can compare these two expressions of the function phi k minus phi j. And the conclusion is like this. Phi k2 wj plus phi k2 bar w bar is equal to this one plus this one plus this one plus higher order term. Okay, let me see the constant term. Here's constant term in some sense, but the left-hand side, okay, which is left? Here's left, okay. Left-hand side has no constant term. So by comparing the coefficients of the constant term, I mean W0 divided by 0, in both hand sides of the equation above, one has that phi k00 is equal to phi j00 holds on each vjk intersection y at least. So this one goes up to define a global function on y. By the way, phi j00 is, by definition, phi j00 is phi j restricted to y because it is constant term. And phi j is pre-subharmonic. So phi j00 is, phi j00's define a global pre-subharmonic function on a compact manifold y. So by the maximum principle, it is constant. There exists a constant a such that phi j00 is equal to a for each j. So this one is equal to a, and this one is equal to a. So this term vanishes. So one have that fkj2 wj plus fkj bar w bar is equal to this one plus higher order term. Next, let us compare this one and this one. Then we have this equation. Fkj2 dwj is equal to phi k 10 dwk, here's k, minus phi j10 dwj on vjk intersection y as one forms. Here, remember, we can show that the function phi j10 is holomorphic on uj. Actually, the proof is very simple. It is enough to show that the above phi j10 is equal to 0, which means for each nu, the derivative with respect to gj nu bar is equal to 0. For this purpose, consider the quadratic equation, quadratic form on C2 defined by this 2 times 2 matrix. It is a special minor matrix of complex Hessian of phi j ww bar, phi j wj nu bar, phi j nu z nu w bar, and phi j zz bar, z nu bar. Very special minor matrix of the complex Hessian. So it is clear that this quadratic form, Hermitian form, is positive semi-definite because phi j is pre-subharmonic. And note that it is equal to 0 because the leading term of this function is phi j 00 z nu bar, but we have shown that it is just a constant. So it is equal to 0 if we restrict it to y. So here is y, here's 0, and here's something. And the determinant of this 2 times 2 matrix is semi-positive because it is semi-positive semi-definite. So we have that this one should be equal to 0. And as a leading term of this function is phi j 1, 0, z nu bar, the lemma follows. This is a proof of this lemma. So, in the previous page, we showed that phi j10 is holomorphic. And also, in the we also have that phi kj2 dwj is equal to phi k10 dwk minus phi j10 dwj. And this one is holomorphic, and this one is also holomorphic. Namely, we had this kind of relation of holomorphic functions. Consider a new local defining function w hat of y on each vj defined by this equation. Actually, this is holomorphic defining function because this coefficient is holomorphic by lemma. Then this one is a system of type 2, since the difference is like this by definition, and this part is equal to this part. I mean, wk square is equal to tkj part by minus 2 times wj square modulo wj cube. And this part and this part comes here, and this part comes here. I mean, only wj appears and higher order term. And as we saw here, this one starts from phi kj2 wj square, and by definition of phi kj2, the coefficient function, this one also starts from phi kj2 wj square. So the difference is just a higher order term. This is a proof of the statement that this new one is a system of type 2. And now we finish the proof of key proposition for m is equal to 1. I mean, existence of the system of type 2. So how is the case in general? Okay. I have 20 minutes. Okay. Let phi j be the local weight function of h with respect to the local frame. This one of y on vj, where we are using a system of type at least 2 because we finished showing the existence of the system of type 2. And let this one be the expansion. The coefficient function of w bar q is phi jpq. And key proposition. In order to show the key proposition, we inductively prove the following assertion m for each m. But it is a bit long, so I summarize it only when r is infinity for simplicity. Assertion m is that there exists a system Vj Wj of type m plus 1. If one uses a system of type m plus 1, the function, coefficient function phi jpq is constant for any pq if p is less than or equal to m and q is less than or equal to m. Actually, we have already shown assertion 0 because assertion 0 states the existence of type, the system of type 1, and because of the assumption that the normal boundary is unitary flat, the system of type 1 always exists. And also assertion 0 says that phi j00 is constant, but we finished showing this. So the proof of assertion 0 is finished. So the next problem is how to show the assertion 1. Assume that the system is of type 2. Then, as the question function phi kj2 is equal to 0 because it is of type 2, it follows that uj phi j10 grew up to define a global holomorphic section of a line bundle. I mean, an inverse, I mean, conormal bundle. Because, as we saw, this one is equal to phi kj2, and now it is 0. So phi j10s grew up to define a global holomorphic section. Holomorphy is shown in lemma. And now the conormal bundle is unitary flat. So it is global holomorphic section of a unitary flat line bundle, so it is constant function. So if we consider the derivative phi j z lambda z mu bar, it is equal to, I mean, it starts from phi 11 and phi 20 and phi 02. It goes phi 01, phi 01 or phi 10 or phi 00 are constants. From this, for any element, xc1, blah, 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 xcd, we have that this one is non-negative because phi j, z lambda, z mu bars are special minor matrix of complex Hessian, and phi j is pre-subharmonic. And in some sense, this one is leading term. By a simple, by a very simple argument, for example, by concerning the integration on this kind of set, we can easily show that this part is also semi-positive, which means that phi j11 is pre-subharmonic. And also, I will skip the details, but by comparing the expressions of the difference phi k minus phi j, as we did in the previous pages, in twofold way, it easily follows that phi j11 also defines a global function on y, and it is pre-subharmonic, and y is compact. So phi j11 is constant. Now we finished showing assertion 1. We will skip the details, but assertion m follows the similar arguments. I summarize how to prove, and the very rough idea to show assertion m in higher m, I mean for larger m, but I will skip this page. Okay, so this is the outline of the proof of key proposition, and as I explained, from the key propositions and Neumann's theorem, Theorem C, the assertion 1 follows. So next things to do is to show the assertion 2 of Theorem C. First, let me explain the relation between the assertion 2 of Theorem C and Osawa's Hartog type extension theorems. Here is Theorem C, but the assertion 1 is omitted. Let X be a compact Kähler connected manifold and Y be a connected non-singular hypersurface of X, so that normal boundary is topologically trivial. Assume that the line boundary Y is C infinity semi-positive. Then the following holds: when normal boundary is non-torsion, the Hartog type extension theorem holds on X set minus Y. This is the second assertion. In this theorem, we consider the case of unitary flat normal boundary. On the other hand, Osawa showed in his paper, or also there are very detailed explanation in his book in Springer's one, I mean Erd's approaches book, that the Hartog type extension theorem holds on xz minus y if the normal boundary is C infinitely semi-positive, but it is not unitary flat. Actually, here he stated only a part of his theorem because he considered a bit generalized situation, including the singular hypersurfaces. But roughly speaking, his Hartog type extension theorem is on the hypersurface y such that the normal boundary is semi-positive, but it is not unitary flat. And my assertion too is for non-torsion unitary flat normal boundaries. So it can be regarded as a variant of Osawa's Hartog type extension. And in the same paper, Osawa also showed another version of Hartog type extension theorem for a bounded domain. In the next page, I will explain the detail. And actually, this Osawa's Hartog type extension theorem for domains, bounded domains, plays an important role in our theorem, in our proof. Theorem Osawa's Hartog type extension theorem for bounded domains. Let X be a compact Kähler manifold and omega be a domain, so that the boundary is a C2 real submanifold of real codimension 1. Assume that omega is locally pseudo convex and the boundary is not Levi flat. Then the Hartog type extension holds on omega. So it is very similar to the divisor complement version. There exists, we assume some kind of weak convexity, but at least in each point of the boundary, in some direction, it should not be flat. I mean, it should have a bit strong convexity, pseudo convexity. By this kind of assumption, also showed the Hartog type extension theorem. Okay, now I will explain the outline of the proof of the second assertion of Theorem C. We will show Theorem C too by contradiction by using psi in the preliminary section. Along these 3 steps. First step, step 1, show the Hartog type extension theorem does not hold on each omega n. Omega n is defined by the sublevel set of psi. Actually, psi is a function defined on x set minus y, and as a by a construction or by condition of logarithmic group, it goes to infinity if it approaches to y. So sublevel sets are, in some sense, the outside of the, what can I say? It is a bit difficult to explain, but I mean, omega n is, if n is large enough, then omega n is a complement of small neighborhood of y. Actually, we will show this theorem by contradiction. So in step 1, we will assume that theorem C, the second assertion, is not true. Step 2, from Osawa's theorem above, it follows that the boundary of each omega n is Levi flat for large n, because otherwise, by Osawa's theorem, Hartog type extension holds. Then show that there exists a holomorphic foliation f on the neighborhood of y, whose leaf is either y or a leaf of the Levi foliation of this Levi flat. Step 3, show that the holonomy function of f along y is u1 rotation. If it is succeed, I mean, if we complete this step 3, it follows that the line boundary y restricted to a neighborhood V is unitary flat for some neighborhood V of Y. In this case, as I explained in the introductory section, for any neighborhood V, V set minus Y only admits constant holomorphic function. I mean, constant function as a holomorphic function. So it automatically extends. So the Hartog's type extension theorem clearly holds. This is the story. Okay, let me explain this. First, I will explain the details of step 1, how to show that Hartog's type extension does not hold on each omega n. Setting is like this. X is compact Kähler connected manifold, and Y is connected non-singular hypersurface, so that normal boundary is topologically trivial. Assume that Y is C infinity semipositive. And also I will assume that the normal boundary is non-tangent. Assume also that the Hartog's type extension theorem does not hold on X set minus Y, because we will show this second assertion by contradiction. In this page, as step 1, we show that the Hartog's type extension theorem does not hold on omega n. Otherwise, I mean, for sufficiently large n. I mean, there exists some positive number such that if n is larger than this positive number, then it is, I mean, Hartog's type extension theorem does not hold on omega n. We will show the assertion by contradiction. Sorry, a bit complicated. There are many by contradiction. But anyway, assume that there exists a sequence n nu, which goes to plus infinity, and such that the Hartog's type extension theorem does hold on each omega n nu. This is denial of this conclusion. Take a neighborhood V of Y and a holomorphic function F defined on V set minus Y. As Y is compact, I mean, here is Y, which is compact, and here is X. And N nu goes, and here is V. But the boundary of, sorry, here's blue. The boundary of omega n nu approximates Y if nu is large enough. So the boundary of V is a relatively compact subset of omega n nu for sufficiently large nu. For such nu, the function f restricted to this part this annulus type area can be extended, because the Hartog's type extension theorem holds on omega n nu. So by patching the extended function f and large f and small f, we can construct the extension of small f, which contradicts to the assumption. That is a proof. Next, step 2. Here we will define the foliation f. By construction, the complex Hessian of psi has at least one positive eigenvalues at any point on the neighborhood of Y. On the other hand, by step 1 Osa's theorem, the complex Hessian of the same function psi has at most one positive eigenvalue at any point, because otherwise, I mean, if there is at least two positive eigenvalues, then at that point, the boundary cannot be a Leb-flat hypersurface. So the complex Hessian psi has at most one positive eigenvalue at any point on the neighborhood of Y. As a conclusion, there exists a neighborhood P of Y such that for any P, the complex Hessian of psi at P has just one positive eigenvalue. Denoted by psi, the Monjamper foliation, I mean the foliation on V set minus Y, such that the leaf direction is defined by the zero eigenspaces of the complex Hessian. So it is Monjamper foliation. It is well known that each leaf is leafwise holomorphic. I mean, each leaf of F is holomorphically image of a complex manifold. But we don't know the transversal holomorphy. So from next page, I think I will skip it, but we will show the transversal holomorphy of the foliation. What is important is this part. Note that each leaf of F is a leaf of the Levi foliation of the boundary of omega n for some n. It is clear because the leaf of Monjamper foliation is the direction that, I mean, if L is a leaf, then psi restricted to L should be polyharmonic. And for any leaf L of the Levi foliation of the Levi flat hypersurface, their omega n, psi restricted to L is constant because omega n is the set defined by psi is equal to n. It is very, very clear. That's why any leaf of F is also a leaf of the Levi foliation of this Levi flat. That's the key point. Here I compute something in order to show the transversal holomorphy of the foliation F, but I skip here. And also, the last part will extend F to V by adding Y as a leaf. And we can also show that it's extended foliation F. So F is a, finally, F becomes a foliation. Homomorphic, non-singular. Dimension 1 foliation on V. That is what I said in this summary part. I mean, F is a foliation whose leaf is either Y or a leaf of the Levi foliation of the Levi flat. What is important is actually this F is holomorphic foliation. Here I've skipped the proof of transversal holomorphy, but I will explain the last part. Step 3, holonomy of F along Y. Let H be a holonomy of F along Y. I think I should shortly explain what is holonomy. Here's Y embedded in X. And take an element, gamma, of the fundamental group. Gamma can be represented by a loop of Y. Take a transversal D, which is a one-dimensional disk in embedded one-dimensional disk which transversally intersects Y or lives around Y. And take also a fix also a coordinate W of transversal D. And consider on the neighborhood of this point, actually this is a base point. Around here, let us consider the leafwise constant extension of this W and denoted by W tilde. And next, around here, let us think about and consider the leafwise constant extension of W tilde. And I extend it leafwise homomorphic way, leafwise constant way, extend it, and we will extend and extend in many times along gamma. And finally, it turns back to define a new coordinate system of the transversal D, if we shrink D if necessary, whose relation is the definition of the image H gamma. Okay. The last part, step 3. Here we want to show that the holonomy of H is unitary rotation. Take a system Vj, Wj of type 1. By the proof of the assertion 1, the complex Hessian of psi is like this. I will not explain the details, but from this, we can say that the linear part of each holonomy function H gamma is unitary constant. And first coefficient should be, or multiplier should be unitary constant. As normal boundary is non-torsion, one can take some gamma such that the multiplier of H gamma is, of course, it is unitary constant, but it is non-torsion element of U1. In this case, we can use Peretz-Markos hedgehog theory. This is the theory on the complex dynamics around the Kramer type fixed point. It is a theory on the one-dimensional complex dynamics. By according to his hedgehog theory, we can show that H gamma is linearizable. It means that by choosing a suitable coordinate W, H gamma is just a rotation. Now the things are simple. Use such a coordinate W and consider delta, which is just a disk. Then the boundary of the disk is equal to d z minus Levi flat, because an orbit settled in gamma, I mean something times lambda should be okay. I will not explain the details, but anyway, by considering the relation between the orbit of the holonomy and Levi flat, Levi foliations, it is easy shown that the boundary of delta is equal to d intersection Levi flat. From this, it can be shown that for any gamma prime, the holonomy along gamma prime is an element of the automorphism of delta. I mean, it preserves. Delta is invariant by any H gamma prime, and it preserves 0 as a fixed point. So it is unitary rotation. That is a proof of step 3. Okay, I'm sorry, it's too long, but I finish here. Thank you.
Okay. Thanks a lot so thanks a lot for the talk. So I don't know if you have some questions. So if there is some questions, audience. Yeah, so there are some questions. Yeah. So as for me, I have one question. So it seems that so for your proposition, it seems that it's so for your key proposition, it seems that it's already very close. So it's already very close to the conjecture. So if we take r equals to infinity, so that means that at least for the local system, we have already we have already a very nice local system for every order. So in the case one, it's from the deformation. type results. So we know that if we have the lifting for any order, in this case we can have the deformation in its. We have the deformation for its neighborhood. So in this case, so in the case of your proposition, so have we some counterexample which says that if we have the local system of any order, then we have some counterexamples such that
yeah. I mean, this one, I guess.
You have already explained it. Okay.
I guess what you said is this. Yeah, other things on the Arnold with as counterexamples. Actually, yeah, as you said, we could linearize the local defining function, transition function of local defining functions in each order jet. But linearization in any order jet, or so-called formal, just a formal linearization, is not a linearization. And this gap seems to be very difficult, but Ueda showed that formal linearization implies linearization when the normal boundary is Tojo. And in not Tojo case, there is such a difficult counterexample. So, but in my mind, I'm not sure, but I guess this kind of counterexample is, for this counterexample, at least X is non-compact. And I guess X is not non-Kähler, I'm not sure, but, or anyway, what I want to say is, if we add some geometrical condition on X or Y, then we can say something more on the relation between formal linearization and linearization. That is, yeah, my motivation. I guess it's a difficult part.
So for that example, it's not a compactor.
At least in this Arnold Ueda's example, X is open surface. And I guess it is non-Kähler surface.
Okay, I see.
I'm not sure, but I guess.
I see. Thank you. So if there is some other questions. So if there is no other, so let us thanks the speaker again.
Thank you.
Thanks a lot for the talk. Thank you.
Thank you.
Yeah, so I think that he had some problems about his micro things, so he could not speak now. I think so. Yeah, so I think that so for Yaden he has some problems about his microphone, so he can.
Okay. I get it. Okay. Yeah. Thank you very much. I'm very happy to have this opportunity. Actually.
Okay. So it seems that so it seems that so for the main difficulty here. So it seems that to prove the conjecture for the yes to if we have the infinity estimal local system, then we would like to extend to its neighborhood once.
You mean extend what? Oh, the name of that. Sorry, I missed.
We would like to extend the local system to its neighborhood. So it's the So I don't know. So for the inverse of the proposition, it's true or false. I mean that if we have the local system for any order, saying this case.
Actually, I'm not sure. I'm interested in it, but at this moment, I'm not sure. Actually, I don't know whether or not there exists a example of line bundle, which is CR semi-positive, but it is not CR plus one semi-positive. Actually, I know there are, I mean, whatever I know, as far as I know, most of the examples are C infinity semi-positive or not C0 semi-positive. So I don't know the intermediate situations, but I'm very, very interested in it because it's really very interesting also in the complex dynamical point of view.